The century-long Einstein-Bohr debate about the nature of quantum reality finally finds experimental verdicts in the 21st century. In 1927, Solvay Conference gathered the brightest minds, where Einstein challenged the probabilistic view of quantum mechanics. Einstein proposed a thought experiment to test whether quantum reality could be complete, not random, a clash with Bohr's complementarity. Bohr argued that precise path information would destroy interference, embodying the wave-particle duality at the heart of quantum theory. For decades, the experiment remained out of reach until advances in precision control brought quantum limits into view. In 2025, two leading teams tackled the century problem, pushing the boundary of quantum measurement to a fundamental limit. MIT, led by a Nobel laureate, used a lattice of ultra-cold atoms to create many tiny slits and probe interference at scale. The Chinese University of Science and Technology team pushed further by trapping a single rubidium-87 atom with optical tweezers. They cooled the atom to its quantum ground state using Raman sideband cooling, achieving remarkable momentum control. The axis in the trap reached near ground state occupancy, enabling quantum-level momentum measurements matching a single photon's recoil. By varying trap depth, researchers tuned the atomic momentum uncertainty and observed the transition from wave to particle behavior. The core experiment entangled a single photon with the atom, encoding path information into the atomic momentum state. Interference visibility: phi follows VLx qua 2, with E as the normalized recoil parameter, revealing the quantum nature of the measurement. The team quantified classical heating noise, adjusting for average phonon number to isolate genuine quantum effects. Phase stability was critical. The apparatus was locked to a 1064 nanometer reference laser with active feedback. Over 10 hours of continuous measurements demonstrated remarkable phase coherence, a prerequisite for clean quantum measurements. The results supported Bohr's view of complementarity, confirming that gaining path information degrades interference. A key finding was the correlation between increasing E and decreasing fringe visibility, tracing the quantum to classical boundary. Their work paves the way for continuous variable quantum information and new tomography techniques for the atomic state. The experiment marks a milestone in quantum foundations and could illuminate the link between quantum behavior and gravity in the future. In a broader context, the 2025 milestone aligns with the International Year of Quantum Science and Technology, celebrating quantum birth and evolution. The Einstein-Bohr dialogue lives on not as a winner-takes-all duel, but as a dialogue fueling future quantum discoveries. Beyond the historic debate, this quantum experiment demonstrates how precise control enables testing of foundational assumptions. The experiment also highlights practical strides in quantum technologies, including quantum sensing and information processing. Future directions include exploring more complex systems, decoherence effects, and potential connections to quantum gravity. The collaboration between Western and Chinese teams underscores the global nature of foundational science. This historic milestone invites broader outreach, explaining quantum ideas through accessible visuals and stories. As we enter a new era of quantum science, questions about measurement, reality, and information continue to inspire. Key researchers include Pan Jianwei, Lu Chaoyang, and Chenming Cheng at UCAS, whose work anchors this breakthrough. The research is published in physical review letters, with figures illustrating the experimental setup and results. In summary, this experiment provides a direct quantum limit verdict on the Einstein-Bohr debate using a single atom and a single photon. The result fortifies Bohr's complementarity, showing how knowledge of one property erases another in quantum reality. The scientific narrative of Einstein and Bohr thus converges with modern quantum technologies and ongoing fundamental tests. With every refinement, quantum experiments edge closer to revealing how the quantum world connects to larger scales and possibly gravity. The study also motivates new directions in quantum tomography and non-classical state preparation for robust quantum computation. As researchers push boundaries, the collaboration highlights the importance of meticulous phase control, calibration, and low-noise environments. The experiment's success may spur investigations into quantum sensing and new regimes and potential links to fundamental physics questions. Finally, the collaboration stands as a reminder. Scientific progress is a global, iterative dialogue across generations and borders.